Introduction to Math for AI Mathematics forms the backbone of artificial intelligence, providing the tools and frameworks for developing, analyzing, and optimizing AI models. Two key areas, linear algebra and calculus, are essential for understanding how AI algorithms work, especially in machine learning and deep learning. Linear algebra for AI. Linear algebra is the study of vectors, matrices, and linear transformations. It is critical for handling high-dimensional data, performing matrix computations, and representing relationships in machine learning models. Key concepts. Vectors represent quantities with both magnitude and direction. Example: a user's preferences represented as a vector in a recommendation system. Matrices represent collections of vectors or transformations. Example: a dataset with rows as samples and columns as features. Matrix operations. Addition, subtraction, and multiplication of matrices are fundamental for computations in neural networks. Example: matrix multiplication is used in transforming input data into features in a neural network layer. Dot product and cross product. Dot product measures the similarity between two vectors. Cross product calculates a vector perpendicular to two vectors, used less frequently in AI. Eigenvalues and eigenvectors. Eigenvalues represent the magnitude of transformations, while eigenvectors indicate the direction. Example: principal component analysis, PCA, for dimensionality reduction. Applications in AI. Data representation, encoding images, audio, and text as numerical matrices for model processing. Dimensionality reduction, simplifying data using PCA to focus on the most important features. Neural networks, using matrix operations to compute weights and biases across layers. Calculus for AI. Calculus focuses on change and motion, providing the foundation for optimization algorithms that minimize errors in machine learning models. Key concepts. Derivatives measure the rate of change of a function. Example: in gradient descent, derivatives are used to update model weights to minimize error. Partial derivatives extend derivatives to functions with multiple variables. Example: computing gradients for each weight in a neural network during backpropagation. Gradient, a vector of partial derivatives indicating the direction and rate of the steepest descent. Example: optimizing a loss function in machine learning models. The chain rule, used to compute the derivative of composite functions. Example: backpropagation in neural networks relies heavily on the chain rule to calculate gradients. Integration, summation of areas under a curve, less commonly used but important in probabilistic models. Example: estimating probabilities in continuous distributions. Applications in AI. Optimization, calculus powers. Optimization algorithms, like gradient descent, to find the minimum of loss functions. Training neural networks. Calculating weight adjustments during backpropagation using derivatives. Probabilistic models. Integration used in Bayesian inference and probabilistic graphical models. Combining linear algebra and calculus in AI. The synergy of linear algebra and calculus is evident in many AI models. Gradient descent. Algorithm. Linear algebra computes gradients efficiently, while calculus determines their direction. Neural networks. Linear algebra represents activations and weights as matrices, and calculus optimizes the network through backpropagation. Dimensionality reduction. PCA leverages linear algebra concepts like eigenvalues, and calculus helps understand variance minimization.